All right. Well, hi, everyone. Um, Welcome to the Alta ML room for the 4 p.m. session. I am Tim Chan, one of the YYC DataCon organizers, and in a moment, we are going to hear Vlad Laukhin talk about machine learning solutions for oil and gas. Please put your comments into the chat box and ask any questions in the Q&A window. Feel free to also upvote questions that you like to be asked, and then we'll have time during this presentation to take questions. We'll aim to finish at about 5 minutes before the hour to allow you to either get back to the floor area, maybe navigate to another room, say hello to people at your table. We do encourage you to live tweet during this event using the hashtag YYCDataCon. Our Twitter handle is at YYC Data Society. We are recording this talk, and it will be available on this remote platform after the event for about 3 weeks. We'll also look to publish the event on YouTube and also on LinkedIn as well. So what I'd like to do now is to introduce Vlad to everyone. So Vlad is a machine learning developer at Alta ML in Calgary. He actually holds 2 Master of Science degrees in petroleum and mining geosciences. Vlad has over 8 years of petroleum exploration and production experience, including petrophysical analysis, geostatistical modeling, and seismic interpretation in shale reservoirs, as well as conventional silicoelastic and carbonate oil and gas plays. Vlad's experience includes research and development of new engineering and applicable machine learning and artificial intelligence solutions for a plethora of industries. He strongly believes that machine learning has a big future in the old school of oil and gas as the industry is getting ready for the upcoming changes. I know I had just enabled Vlad. Let's see. Vlad, are you able to take the stage right now? Okay, 1 second here, and we'll work out. There we go.
Sweet deal. Thanks, team.
Okay, wonderful. Really delighted that you're here, Vlad, and the stage is all yours.
Sweet. Thank you very much. So, sorry. Hello, everyone, and welcome to the DataCon. It has been a long day, and I hope that you won't fall asleep while I'll be presenting today. So my presentation is called Machine Learning Solutions in the Oil and Gas. Pretty broad and interesting topic, I must say. Though today I would like to discuss 2 actual problems that have been solved for our clients within machine learning perspective. So the first problem focuses on predicting drill bit damage, wear and tear with identifying related vibrational modes. And the second problem is centered on optimizing pop-down operations to minimize non-productive time on site while maintaining operational safety and minimizing equipment damage. I'm gonna give the first talk, and if we'll have a bunch of questions, we can answer those and then continue for the second talk. And if there won't be too many questions for the first topic, we're gonna go straight ahead. So the first project was done for Cougar drilling. And I would like to talk about this problem a bit more in detail. So it has been centered on predicting drill bit damage, wear and tear, with identifying the related vibrational models. It is like Cougar Drilling is an oil production and service company dealing with hundreds of wells per year, drilled and completed. Recently, they have started working on a new tool that will be detecting the wear and tear of the drill bit and they were looking forward to identifying different vibrational mechanisms and damage that damage the drill bit, utilizing their sensor data installed in the drill bit. And they contacted AltaML for utilization of the machine learning solution. Currently, the system is in R&D, and we are helping them with lab and field tests. This problem solution will help to minimize non-productive time on a well site caused by the pull-out operations to check the drill bit. It will also ensure operational safety and minimizing equipment damage for the client. So a little bit about the background. So why drill bit wear and tear problem? It can add up over the lifetime of the bit. Replacing bits is expensive. It is hard to detect during the drilling operations only within the technical pull-out of hole or by the technical calculated schedule. Identifying bit problems as soon as they occur or predicting them ahead of time can help save on these costs. Couple words on the input data for this problem. In this use case, our team had records of the bit's position, acceleration, temperature, and battery with the downhole tool, containing a set of sensors. Downhole BHA simulator lab data was used to deliver the initial model. We utilized two approaches to build the model, model in time domain and frequency domain. In addition, there was a requirement to test out the sampling frequency to save the battery life on the tool as it works wirelessly. Each experiment is run on a different sampling frequency with the goal of finding a minimum suitable sampling rate. Continuing on, a couple words on the stack we used. Here we used pretty standard set of packages available in the data science market. Only like SciPy was utilized a bit more in detail here because we had to write our own kind of additional package based on the SciPy for the optimization kind of problem for this one. Okay, so data feeding approach. When talking about the time series data of sensors, usually in order to work with them, we create 3D stacked tensors that are fed into the time shift step, but for frequency domain, we need to use 2D stacked tensors because it has been already framed, and then we aggregate the signal amplitude and other attributes with PCA to identify best set and then feed into the model. Usually we are running the RNNs for this one, but for this specific kind of problem, we used a bit more in detail approach with the LSTMs. So why frequency domain? As I mentioned, we utilized two strategic approaches on how we treat data. One of them was data feed in frequency domain. Firstly, if transferred to frequency domain, vibration mechanisms display significant difference in frequency content. Frequency content can be recorded in Windows, and only important frequencies retained for the model training. Upsides of this approach, we can use multiple features and can model multiple features independently. It accepts 3D time slices. Downsides, we require consistent sampling frequency, but it is something that A, drains the battery more quickly, and B, requires appropriate sampling to be implemented. Second approach that was used in the data feed was the time domain. Modeling time domain in Windows via RNNs is really successful in other type of time domain problems. It can retain good metrics with uneven sampling, can go much lower sampling frequency than frequency-based approaches. And frequency approaches are capable of about 10 millisecond rate per acceptable metrics. So a little bit too into details here, but main thing about this is that time domain is more kind of acceptable for the battery life for the sampling rates of the tool, but it's less acceptable in terms of accuracy of the prediction. Okay, so model training approach that we used for this problem. Dealing with the serious predictions, like data scientist is usually looking at the RNNs or LSTMs to solve the problem. RNN type network, they accept 3D time slices. Past behavior can influence prediction that happen in the future. In other words, they pose time-based memory. A little bit into detail here is that RNN is not the best solution. So the best solution would be utilizing a set of RNNs with the LSTMs. So GRUs and LSTMs are generally better than regular RNNs at longer term dependencies that we are trying to predict in the future. So our MVP results that were initially delivered to the client in here, like we on the left, frequency domain approach can identify vibration anomalies with around 10 milliseconds sampling rate, even when some sensors stop working. With the time domain approach, we can identify whirl and torsional resonance vibration anomalies with the 50 millisecond sample rate on a set of sensors. Lower sampling rate is generally more battery saved, and that means that the operational time is longer. More resolution in the frequency domain approach, less sensors needed, and we are able to withstand more damage for these, like for the bit itself. And a little bit on the demo side here about our tool that we delivered. So basically, when we are running the drilling operation, our gyroscope, for example, is showing some results. The tool is recording that there is no kind of anomaly here. And then at a certain point, we see that there is something wrong is going on. And that's where we are detecting this kind of problematic thing that is causing the deterioration of the drill bit. So sorry about too technical things, but if you have any questions for this one, we can go ahead. Okay, I got it. It's not that interesting. Let's get to the next one then.
Come through. So if you want to take one, some of the those input channels are conventionally used for depth interpretation. Have you applied any of those algorithms to generate other input layers at depth?
Well, we've been playing around. We've been playing around with a bunch of solutions that that will be incorporating a bunch of other information inside of the problem. Most of the time we were using like laboratory tests, and we were thinking about implementing a little bit more in detail kind of analysis.
Okay. And then there's just maybe one more, and you can decide if you want to take this one now or maybe afterwards. It's about going over, sorry, how do you solve the sparsity issue? So missing lots of data. If you could just go a little bit more in detail about that, how you overcame that.
Okay, so in this kind of set, we didn't have problem with the data. Data was clean and it was labeled, and we just we're trying to play around with the models that will be given the best kind of results that we want to achieve. And problem came out when we started to work with the field tests, And then that's where we started to get a bunch of other vibrational patterns that we didn't see in the laboratory things. We had to deliver like a bunch of supplementary attributes from the frequency and bunch of supplementary information from the drilling operations records, like penetration rate or our ROP and other records into the data to see how, like, and performing the PCA or other dimensional reduction analysis to overcome this kind of sparsity thing.
Mm. Okay, no, thanks for that. And maybe, just even stepping back, what does the algorithm predict exactly? Is it like the cumulative amount of damage that the tool?
It's basically telling you whether the drill bit at this point is experiencing this certain pattern of the resonance. And then the engineer is already knowing that if it's like a torsional resonance, we're gonna have this type of damage. If it's a whirl, we're gonna have this type of damage at the end. And we want to operate within the safety limits. So basically, either you're decreasing the load on the beat, or you're decreasing the rate, or a spinning rate, or other things. So basically, it turns into optimization problem once you have the anomaly labeled. Our part was the anomaly detection here, and potentially we're gonna be doing the optimization for this kind of set too, after
Awesome.
it's rolled out in the field, like 100%.
Great. Okay. Well, that's awesome, Vlad. No, thanks for taking some of those questions. Yeah, maybe let's go on to the next part of the presentation.
No problem. Okay, so the next one was for the company called Tier 1. And this problem was centered on optimizing pump down perforation operations for oil and gas service company. Tier 1 is the wells completion company dealing with the 1,000 completions operations per year. And they were looking to solve the non-productive time problem for their perforation jobs, and decided to get the machine learning solution for utilizing AltaML perspective. This problem solution is helping to minimize non-productive time on a well site, and it will also ensure operational safety and minimizing equipment damage for the client. A little bit on the background. So there were three main interests for the client in this project. First one was to perform pump down operations faster. So the more vivid the completion, the faster the well is transferred to the frac team, reducing non-production time. The second goal was to increase their competitive rate by reduction of the operational costs. So the more consistently a company can perform this operation, the better their competitive advantage. And the third one, certain value point, was decreasing the non-productive time. By doing so, the client can accomplish more wells in the same time period. This significantly increases potential revenue for them. Talking about the stack, the stack we used in here was pretty much the same as for the previous task. We utilized standard ML and deep learning libraries like TensorFlow, sklearn, and other. The only difference here was that we had to improvise with the data processing, as the input data was considered highly messy. And we had to use some libraries for string matching to get the appropriate UWIs to match NLTK and fuzzy match that we used. Also, we utilized some deep learning approach to get the input data QC more efficient. For the optimization part, we used SciPy, NumPy, and Dask with pandas for data manipulations. Okay, so diving into a solution, I would like to throw a couple words on data processing for this project. One of the biggest challenges of doing machine learning in oil and gas is data readiness, and this was a nightmare for us for this company. Due to the nature of operations, most of oil and gas service companies do not have an operational database. So storing different bits and pieces of information is mostly done on gazillion folders on their PC, Excel files. All the data sources are coming from different applications, from different client companies and sources. And sort of cherry on the top of the cake is naming convention mismatch between those UWI tracked by the office and field workers. So our case was not that different. As I said earlier, the client is dealing with 1,000 operations per year, collecting terabytes of wireline recordings per well. Each well had up to 60 completion stages in it. Each completion stage is represented with a feature vector composed of pressure at the wellhead, inclination, tension, speed, pump data, and you name it, and other metadata associated with each run per well. Each stage had lengths of 30 to 60 minutes to finish, with the sampling rate each 10 centimeters. So in order to solve these problems, we had to develop a data cleaning and prepping pipeline that utilized some text-image data matching to perform the appropriate QC before constructing the model. We used fuzzy match and LTK to find similar well names between data sources, and the approximate near neighbors algorithm used in Spotify vector matching to map the different speed, tension, and inclination profiles to fix the data readiness. Yeah, so a bunch of algorithms like annoy, C++ libraries, Python bindings to search for points in space and that are close in a given query point. So basically like a bunch of things to mitigate the data problem here. Okay, so once the data was clean and ready, we continued constructing the pipeline. The next stage was to figure out the wells that are most similar to each other. Although in the real world, we would have to incorporate the data about all the factors affecting operation, at the time of this experiment, we didn't have any geological or geophysical data available, so we used inclinations and TVD as the reference. Our guideline was that most of the wells the company works on are up to 94 degrees of the inclination. Each well is usually broken down into 3 zones depending on its inclination angle. The first zone, steep vertical section, where the inclination is around 0, so around here. This zone can be several thousand of meters long. Second zone, where the inclination angle starts to build up in a rapid manner. So basically like from 2 degrees to 85 degrees within 100 of meters. And the third zone, around 90 degrees. So utilizing this information, we developed an algorithm that tracks the change in the direction of the wellbore over different lengths and breaks it into zones based on the inclination profile. The next step was to cluster all the wells to prepare appropriate optimizations for each cluster or similar wells. Here we used unsupervised learning algorithms for numerical data clustering. We tried a whole bunch, hierarchical clustering, GMM, spectral, k-means, etc. And k-means proven to be the best for this problem. One of the approaches we tried was also building a visual cluster utilizing transfer learning algorithms, where we build a deep net image classifier for the well shapes. This turned out to be less effective than the k-means based on the data input. Okay, coming to the solution. Our solution here was testing 2 different approaches. The first approach was to solve the problem with the genetic algorithm, where the model takes the best ML predictor. In our case, it was random forest trained on historical data, the system maximizes line speed output and minimizes the time based on historical parameters of the input data. The implementation steps that we had, the first step was to build the ML predictor for operation speed with most accuracy, constructing a production formula for a speed, talking in the economic terms. This general predictor was holding the memory of all historical operations on the specific well clusters. And for the sake of this experiment, we used random forest with grid search that would take the predicting and dependent variables as the input and train models for the future predictors. And second implementation step, we create the genetic algorithm implementation. And the output of this genetic algorithm is a value of the dependent variable based on the interactions between predictions within the genetic algorithm and predicative result of random forest regressor. Sorry about so many technical terms. This will include a bunch of functions to calculate fitness value, selection function that selects the best individuals in the current generation, build crossover function, and build mutation function that changes a single gene in each offspring randomly. So it's basically a bunch of internal kitchen for a genetic algorithm building into the whole project here. This approach took the independent variables, predictors built on top of the historical data, and two values of speed and tension to output the optimal value for the driver, for the worker that is running the tools inside of the well bore. Okay, done with the GA and finicky approaches. One could ask why we need to make the optimizer if we can just push the full gas and run as fast as we can. But what about the cops around the corner? To identify those, we utilize the second approach, where we use statistical inference of all the operator runs per each cluster. We used historical performance of the well operation, like speed, tension, and the pump down of water inside of the well. We calculated the most dense points in the distributions per the same well cluster, and then trained the model capable of guiding the operator in the optimal working zone. Plus, we can now add wear and tear features into the model, characterizing equipment wear and tear for the wells of the same shape. The output of this run was a trained ML model based on probability distribution. So basically, like we took all the runs within the same cluster of the wells, and based on the density function per each meter measured, we built like a baseline model that is tracking down the densest points of the acceptable levels where we want the operator to be run in. The output of this run, as I said, was trained ML model based on probability distribution. Here we are with the rolling window with smoothing applied, we can see the median and predicted value for the optimal run superimposed onto the identical runs of the wells in the same cluster. So basically the same kind of approach that historically operator would use with their experience. So basically the experienced guy will run into more optimal value, and then less experienced guys are working within the limits that are below or above this optimal value. All right, so as I mentioned above, the use case was to utilize historical data on perforation and well inclinations to perform analysis and propose an optimal speed value recommended to follow during the course of operation. Utilizing the historical runs, we were able to train the model that is capable of guiding the wireline operator in a cruise control manner. The guidance is based on the historical data, distributions per each group, and other parameters. So for each point in time and the depth of the well, our system predicts the optimal speed value the operator should run with. So basically, like we built the PDF, the probability density function, and transformed it into probability of risk. So it's 1 minus. And then we took the quantiles of these distributions and build the system that is tracking down where you are inside of the well bore, and then what is the optimal value that you have to run based on these historical runs within this certain cluster of wells that your well is inside of this cluster. So it's kind of hand and glove problem here, I guess. All right, so if our model, if run on the historical well simulations, is capable of reaching meaningful time saving results. So basically, we estimated time saved between the median of the run to the predicted values of around 14% for rigging hole and 10% for pull out of hole. And talking into numbers here, it's a matter of maybe like 10 minutes per well, and 1 minute of the downtime for the client is costing at least $2,000. So basically like 10 minutes for a run, I mean, for a well. So basically we have 60 runs, and then we are saving 10 minutes per each run, per each well, and it turns into like more than $1 million a year saved for this client. All right, so I guess I'm pretty much done for this presentation. So if you guys have questions, I'm more than happy to answer them.
Hi, Vlad.
Hi, Kazim.
I have a few questions in the Q&A session, so probably they might be from your part 1 of your presentation. So it's, yeah, let's see if you can answer them. One of the question is, can you please describe in more detail how cluster labels were used to predict the optimal speed?
Mm-hmm.
What were the features? What was the response variable for your model?
Mm-hmm. Okay, sure. Let's do it step by step. So the first question is that what features we used? The input features were the speed and tension and pump down of the water, because the well is horizontal. They're pushing the tool set with the water inside of the well bore. And we got pressure, I believe, on the wellhead, and the pressure down the hole. And that's what we were using to predict the optimal solution here with the genetic algorithm optimization and the machine learning, because we needed to predict a bunch of features based on the input parameters and then run the GA on these features. And what was the second question, Kazim?
It was what were the features and what was the response variable for your model?
Okay, so we were trying to predict speed as the kind of target here. Actually, we built 2 models here. We are trying to predict the speed and the tension, because it's a 2-way problem. Either you're predicting the optimal speed and optimal tension, or you take the historical value. So for this first approach, we were predicting speed, and based on this predicted speed and all the other operations, we also were predicting the tension that is more or less capable of doing this optimal solution. Although I have to say is that due to the limitations of the data set, we decided not to utilize that into the production. This kind of hybrid ML with the optimization kind of set was not appropriate for the client, because it was not given the right results. Like, it was given the okay results, but we could achieve better results with other approach.
Thank you for that.
No problem.
There are two more questions, which I'm going to pretty much group together, and they relate to your first part of the slides, I guess. Is it possible to predict the breakage of tool bit before it even happens? And the second part is, which pretty much I asked, is that if you were able to predict the breakage, then were you able to differentiate between formation change or some other outside variable versus the bit deterioration?
Okay. In terms of the first thing, we can definitely predict whether the bit will be deteriorated and done within certain time, like because we can identify the resonance patterns within the working operation. So basically on this picture here, so like we have a normal standard operation where it's blue and then it turns into red, where we see the labeled kind of predicted anomaly here. And then just by knowing that we are dealing with the vibrational pattern, we already can expect what type of damage we're gonna expect. So each type of resonance, vibration resonance, will be giving you different damage, and we can definitely look into it and predict what type of damage we're gonna see within what time, based on the drilling parameters that we are using. So it's like R&D stage right now. We didn't go into much detail. We are still working on that, but it's kind of a really interesting kind of scientific
it does look interesting.
Okay. And in terms of the formation analysis, we didn't, like, this was not our kind of task that we were looking at, but definitely we were trying to get some external data from mud loggers to get into, incorporated into this detail. Plus, like I was asking them to send us some well logs as well, just to increase our information set. And like definitely in the future, like we'll have to accommodate for the fascists and then for the other like input parameters for the like system that we are working in.
Okay, nice. And this system failure can be detected early, and you can differentiate between some outside parameters like a formation change or something like that?
Well, ideally, yes. Ideally, we would like to see the formation change in it. But in this kind of exercise, we were aiming to decipher only the resonance patterns of the drill bit inside of the wellbore.
Okay. So it's still in progress.
Yes.
Nice to know. All right. So there's another question, but there is an acronym. Do you use FFT for future engineering? So I'm not sure what the FFT over here and means.
I'm not sure as well. Whoever texted that. Could you please explain?
Yeah, so we will go in more detail if you can just put more detail in the question, and whether it's from part 1 of the slide or the second part, then we can, I will ask it again. Moving to the next questions. Do you have to consider the physics in your prediction, or do you just use the data to generalize your prediction?
Or actually, can I come back for FFT? I got it. It's a Fourier transform. If I'm right, yes, fast Fourier transform. That's what we are using for the frequency analysis. Yes, that's the answer for the previous one. Sorry about that.
Right.
What is the second one?
So, did you have to consider the physics in your prediction, or did you use just the data to generalize your prediction?
Okay, so it's a pretty interesting thing. For this specific Cougar and Tier 1 problem, we didn't use that. We didn't accommodate for physics kind of setup, but we have been working with GIS companies that were doing some kind of ionosphere modeling we were trying to increase the accuracy of GPS measurements where we had to accommodate for physics. That's one thing. And another one, we've been working with the geotechnical company that was building the helical piles setup, and we had to incorporate the actual load and shear, and we had to look into the physics of this process inside of the model that we're predicting for them. In terms of these two use cases, we didn't accommodate for physics here because most of the data was coming from the laboratory. We couldn't accommodate bunch of other variables that are coming from noise and from other unexpected sources. So that's something that was too complicated for us because we didn't have too much information. We were missing too much data there.
Sounds good. All right, moving to the next one. From your experience, how many failed drill bit sample was enough for you to model, for your model to generalize?
That's pretty complicated because we are still in R&D. Most of the work was done in the laboratory and then they put it into the field, and we only had maybe two samples, two records, full records for the actual drill in the field. So it's just work in progress right now. Nothing specific for this one.
All right. Thank you, Vlad. If there are any questions from the participants, you can just write it in Q&A. Otherwise, we will be closing in a few minutes. Any questions? I don't see any yet. So I will let Tim handle it from here.
Wonderful. No, thank you, Vlad, for your very insightful presentation. And also thanks to those who attended and for posting those questions. So that brings us to the close of this particular talk. Shortly, you'll be heading back to the floor where you can maybe spend some few moments connecting with people one final time. And then at 5 o'clock, we're going to be back in this room here in the Alta ML room where we will have our closing remarks. And then after that, we wish everyone a good night and we'll see you tomorrow morning. But please do spend the time. Vlad will also be on the floor as well too. So if you want to stop by and just connect with him, and then do hang out until 5 o'clock. We do have our closing remarks. And I do believe that just right after the closing remarks, we'll have some prizes to give away. Okay, so with that, thanks everyone, and we will see you shortly.
Thank you, guys. Have a good day.